5.8 formulas. So this is just manipulating formulas to be what you want. Like, for example, if you're to look at the area of a rectangle, which is length times width, you can use principles of equality to solve for, let's say, the width, right? You could say the width is the same as area divided by the length. So that would be useful if they gave you the area and the length, but not the width. And you could find that if you wanted to. That's a very basic example, but that's kind of what we're doing. We're going to take a formula that's given and manipulate it to be what we want it to be, or what they tell us for it to be. So to do this, we're going to need some principles of equality here. Just principles of equality says whatever you do to one side, you got to do the other side, okay? Now, we know from the past that addition and subtraction, we use those two principles of equality if we see addition and subtraction with the variable we're solving for, but we do this to make make zeros, okay? Now, why are we making these values zeros? It's because if we can make them zeros, we get to ignore them. Kind of like people that are zeros, you know what I'm saying? We just ignore them. So the other ones we have are multiplication and division, like this. That is usually to make the coefficient, or sometimes coefficients, in this case for today's lesson, ones. We make ones with this, right? Now, usually, in fact, to make ones, we usually just use division, but multiplication happens from time to time. From what I remember, I don't remember seeing any distribution, or, well, there probably is going to be some combining like terms. But also, we now have to consider some factoring involved to sometimes yank out the variable that we're solving for, and so we can isolate it, okay? So principles of equality really are meant to isolate the variable and then to get that coefficient to be a 1. So isolating is usually with addition and subtraction, but we can use multiplication or division for isolation as well. And then, of course, factoring, yeah. This says, we got two A's in this, by the way. We got a large A, uppercase A, you got a lowercase a. It's solving for the lowercase a. Now it says solve A equals 1/2 H times A plus B. I believe that's the formula for a trapezoid, the area of a trapezoid, if you care. But it's A, right? That means in the end, we need the equation to read A equals something. In fact, I'm going to reverse that and make it A equals something. Why am I putting A on this side of the equal sign? Because it's on this side of the equal sign. And I think I can deal with that, okay? So to start us off here, what I would like to do to isolate this A is I don't want this garbage right here. Now, some students are like, I need to distribute that stuff, don't I? You could. I just don't want to, so I'm not going to, okay? So, but I'm going to make a 1. I'm going to make two 1s, but one at a time. So first off, right, principles of equality, whatever I do to one side, I got to do the other side. The 1/2, I'm going to multiply by 2, but if I do it to one side, I got to do the other side. That's kind of sloppy, but it's best I can do. So that is now on the left, I got 2A equals, and here's the 1, right? I got 2 divided by 2 is 1, and then we got the rest of that, which is H times the binomial. So that's the first one. The second one is where I'm going to take the H and make it a 1. So I'm going to divide the H. Well, I'm going to show the division a little different, actually. H, I'm going to divide it by H. But if I do it to one side, I got to do the other side. So on the left now, I have 2A over H, which is going to equal, well, that became a phantom 1. And even though the A plus B is in parentheses, I don't really want it in parentheses anymore. So I'm not going to use the parentheses. I don't see anything that can be distributed or factored out there. Now, we're pretty close. Okay, we're pretty close to getting A. I just don't want the plus B right there. Garbage, right? So last thing I got to do now is get rid of that B. And I'll do that by subtracting B. Now over here, I'm kind of putting it on the right just because I feel better that way. But on the left side, I've got the 2A over H term. And then that was minus B. Sorry that B looks like a 6. But we did zero out the B, and then we're just left with the A, which has been dropped. That's what we wanted. We just wanted it to be A equals some garbage. It looks like garbage, but we got to get used to it looking like this right now for this lesson, okay? Because we're used to seeing just A equals maybe some number, maybe two numbers, but now it just equals some kind of looking expression, I guess. This equation that we started out with, it's the same exact equation right here, just written differently, that's all. And by the way, some of you guys are like, I want to just make that common denominator. So another way you can do this is 2a minus bh all over h equals a, and that's the same thing. I don't really care how that happens, but some students know how to do it. I just recommend stopping right there because it's less work than to make this common denominator stuff. Manipulating formulas. So this just, again, it's a kind of another way to say what we just did right there. Sometimes though, the variable is in the denominator, which we don't want. And so what do? It says LCD, lowest common denominator. The truth is that it really just needs to be the common denominator, right? So however you get a common denominator, the nice thing about that is you get to remove all denominators, and then you look at an equation with no fractions. And fractions we don't usually like. Fractions have been known to destroy people's lives, so we try to avoid them or get rid of them if we can. Use the distributive property if we need to get rid of some parentheses. We'll combine like terms if it's needed, and then move the specific variable to one side of the equation and all of the terms to the other side. Sometimes, so we need the variable that we're solving for on its own side of the equation, but sometimes you'll have two terms on the same side of the equation. The reason why you need that to happen is so you can factor it out so that it becomes its own term. I think we'll see that. It says use distributive property and multiplication property of equality to get the specified variable alone. Yeah, we'll see. So we're going to solve for r. That's good. Now, like I was saying, what we would like first is to get common denominators everywhere. Now, even though they're using the same variable r, it's r1, r2, and then a non-sub-value here. So I've got a regular r. I'm going to start on the left and I'm going to make each denominator at least have an r. So this first, the r1, it's missing an r, so I need to multiply both the denominator and numerator, right? But then the r2 is missing it as well, so I'm going to multiply r there and then multiply it in the numerator too. Okay, so now I've got at least an r in all of the denominators. That's matching, but they're not still completely matching, which is what we need. Next, I'll do an r1 right there. So r1, it's missing from the first term there, so I'm going to have to multiply the r by r1, but it's numerator as well. And then the r2 is also missing a multiply by r1. But again, if you do it to the denominator, you got to do it to the numerator. So all the terms have a denominator of r and r1, but now we need them to match with r2s as well. So I'm going to have to multiply the first term there. I'll multiply it by r2. And even though the order is different, it doesn't matter because it's multiplication. Yeah, it's great, right? So r2 there and the middle term as well. Okay. So I have got a common denominator all throughout, and since I have that, now I can rewrite the full equation but without any denominators. So I'll put this in kind of its proper order, I suppose. R1, R2, R1 times R2 really, equals R times, I'm going to skip the 1 and just make it times R2 plus the R times 1 times R1. Okay, well that's good, but what the crap are we solving for here? I should have mentioned that. We're solving for R. So I got a couple R's, regular R's, right? I've got this R and I got this R. I don't want two different R's like that, so this is where we got to use, like I was talking about, we got to use some factoring on this. So from those two terms, I'm going to factor out an R, and that would leave me with the parentheses, inside the parentheses, an R2 plus R1. And this still equals R1 times R2. It's not a comma, that's a 1. We're actually pretty close at this point. I'm going to call it a coefficient of R, and it just doesn't look like a regular coefficient, right? Just like our expressions, our answers, they're not looking like regular answers. R2 plus R1. I need to get rid of that, but it's being multiplied by R. The good news is that to solve this, now I got a principle of equality, right? Because I've got an individual R. I can make it all by itself, though, by dividing this side by R2 plus R1, and this side by R2 plus R1. So what do I get? Well, I got R1 times R2 all over R2 plus R1, and I'm sure you probably noticed the order doesn't matter for the addition, but either way. See, and this whole value right there became a phantom 1 for my R. Done. Because we solve for r. It's r by itself. R equals something. And as strange as it sounds, it's exactly the same equation as the one we started with. It's just shown differently, that's all. Yeah, sorry, I probably should have put those parentheses there. Maybe that would have helped to see that we're dividing the same thing by itself. Just whatever you do on this one, again, a common error, because this is very new, right? It's like, what the crap, we can divide both sides by binomial? Yeah, of course we can. That's the nice thing about the principles of equality. But some students tend to just be like, well, I'm going to subtract R1 here, and then I'm going to subtract R2 there, and get something. It looks pretty similar, but it's not the same. And it needs to be the same. So this one says solve for B. Why don't you guys try this one out? Try it out. Take a minute. You know, just give it your best shot. Again, it's new. I wouldn't expect you to get this on the first try because it is new. But if you do, that's great. If you don't, just give it a good go the first try. Okay. Now, the first thing I noticed is we got these two denominators right here. Now, be careful. Take your time on these, right? Like, try not to rush yourself. Think about what you need to isolate the variable. The good news is it says B, right? So we do know that in the end we should get B equals something. Well, I guess maybe I'll put it on this side. B equals something. The problem with this right now is that the -8 does not have a denominator, B. Right now it has a denominator of 1. So I'm going to have to multiply that 1 by a B. So the 8 also multiplied by B, okay? So, I don't know. I'll rewrite the full equation right now just so we can see what happened right there. H over B minus 8B over B equals -3F over B, right? But now that we have all common denominators, I can get rid of them. So I can now show this equation as just 8H minus 8B equals -3F. Now, to isolate my B's right here, my -8B's, I want to get rid of that H. So I will, by using a principle of equality, I'm going to subtract H from both sides. And I am purposely offsetting the -H there from the -3F because they're not like terms that I can combine. That zeroes out the H's. I can now drop my -8B, which equals -3F minus H. The last thing I need to do is to get rid of that -8 coefficient of B. I want it to be a phantom 1 right there, phantom 1. So I will take that -8 and divide it by itself, -8. But if you do it to one side, you need to do it to the other side. That's phantom 1. And I'm left with -3F minus H over -8. And yeah, at this point, some of you guys notice, okay, there's a lot of negatives right there. The -8 can really get rid of the negative and then the minus. So if you wanted to, you could write 3F plus H over 8. That's more work than I'm going to do, though, so I'm done. That's it. Same exact, by the way, this is the same exact equation as this one, just written in a different way for B this time. So this one, it says to solve for J. Again, where's my J at? It's right there. It's in the denominator. And since I have denominators, I'm going to force all the denominators to match. There's 3 different denominators, so it's a little bit of work, still doable. All right. So again, I'll start with the left. I got the U, so the X is missing a U. So I got to put it in the numerator as well. I don't know if that was a better U, but whatever. The J also is missing a U, same with the numerator there. So U times 5 as well. So I've got U's all throughout. Now, next I'm going to go to my X's, right? So I've got the X from the middle term there. The U is missing an X, so I got to multiply in the numerator. The 5 over J also missing an X. So I got to do it in the denominator and numerator. Last up, we got the J in the last term. So the middle term there is missing a J. Same with the first term there, missing a J. So that I don't have to write so much. I'm not going to rewrite this, even though it is very colorful. But I now have 7xj equals, well, I'm going to make it 2uj. I like the numbers in front, but you don't have to. Plus 5ux. Now here, my problem is that I got j's on both sides of the equal signs. I don't want that. I want them on their own side. I'm going to force them to be on the left side of the equal sign. So now, the 2uj, let's go ahead and zero that out. Because again, this is just in an effort to get the j's on the same side. So I got a minus 2uj from both sides. Now, again, you see I'm offsetting this negative 2uj from the 7xj because they're not like terms. They have j's, but they have different x and x and u's there, I guess. So now the expression becomes negative 2uj and then positive 7xj equals, well, we zeroed this stuff out, so we can just drop the 5ux. All right, now we're in a situation like we had a couple of problems ago, where I've got two j terms, but I only want one j term. So I'm going to take that and I'm going to factor out a j from both of those. Then I'm left with a negative 2u and a positive 7x. And yeah, this still equals the 5ux. So close, we're so close. The last thing we need here is just for the final expression here to just be j equals, right? So principle of equality will do that for us. Take both sides and divide it by, again, I'm going to use the parentheses, hopefully that helps. Divide by negative 2u plus 7x, but it's got to be on both sides. So divide by, I'll put this one in parentheses, but I won't in the final answer because you don't need them. You can, by the way, like the assignment should take the parentheses if you want it, but I got 5ux over negative 2u plus 7x. And that is all. By dividing that by negative 2u plus 7x, that really is a phantom one right there now. Some people say it cancels out, but it's a phantom one. Okay, so this one, again, principles of equality should do it. Technically, we could do this with several principles of equality here at once because I don't see any addition or subtraction here. It's just a lot of multiplication, a lot of division. But first, I'm going to get rid of that 5. My instincts tell me to do this with cross multiplication, but geez. I'm going to make the common denominator things, then I can ignore that 5 denominator, right? So like the m really is just m over 1. So I'm going to multiply that by 5. But if I do it to the denominator, I got to multiply it by the numerator. So this would give me 5m. You could say over 5, but again, we have common denominators. 5 times 1 is 5, and we got the 5 common denominator. And so this would equal the numerator from the right side, 11r squared times h. So this is all in an effort to just solve for r. And actually, we're pretty close. It's just that it's r squared. I'm going to solve first for r squared. And so here, what I would like is to take the r squared and just have it by itself. Okay. What this also means, just the way that this is written, is that I'm going to make the 11 a 1 and the h a 1. Because those are being multiplied, I'm going to have to use the division principle of equality to force those to become 1s. So I'm going to divide there. I'm going to divide 11 by itself, but if I do it to one side, I got to do it to the other side. That would be a 1. And then the h also, divide it by itself, but if you do it to one side, you got to do the other side. So there's a phantom 1 as well. Again, I made these phantom 1s. They're there, by the way, you just can't see them. And now on the left side, I now have 5m over 11h. Last thing here that I want is a r, not r squared. I want it to just be r. How do we get rid of a, yeah, you got it, right? Maybe I'm talking too much, but yeah, you just square root both sides. Square root of a square is just, there's a phantom 1 right there. You just don't have to show it. And then we got the square root of 5m over 11h. Boom. All right, direct variation is also known as proportional. I don't know if that really helps. But the nice thing about direct variation, proportion, I think I spelled that right. You have a proportional constant, which is also the constant of direct variation. Why do they call it two different things? The same thing, two different things. It's because it makes us math people look smarter than we are. If you can become a math nerd like we are, then you can look smarter than you are too. But until then, you got to work on it, okay? Now, usually we would set up direct variations as a proportion like this one, and it's legitimate to do that. On the other hand, you can find the proportional constant. The proportional constant, if you remember this stuff from back in like 900 or 950, it's also known as a unit rate. If it's a unit rate, then it just has labels, right? Like miles per 1 hour, or dollars per ounce. You see what I'm saying? One of the ones is one of the values is a 1. Okay. And then if you wanted more, like if you knew that you were paying 25 cents per egg, and you wanted to know how much a dozen was cost, you'd multiply 25 cents by 12, and then you'd have the cost of a dozen. I remember when they were like 99 cents. But in any case, the reason why I'm bringing up the proportional constant K is because we're going to need it when we get to joint variation, which it's worse than it sounds. Then K equals Y divided by X. Usually what they'll do is they'll show it as like X equals KY or something like that. Maybe I got those switched. I guess it'd be Y equals KX. Yeah, that seems better. And then you manipulate this equation for K, which is your proportional constant, just to get you prepared. This one says Y varies directly as X. And this wording right here, I hate it. I don't know who wrote it that way, but some math nerds at some point was like, dude, watch this. And they did it, okay? I don't have any control over that. It's just, all we're concerned about here is that it varies directly, and then we know it's a proportion. Now, I'm going to do this 2 ways, all right? So I am going to set up a proportion, which means you have 2 fractions that are equal. All right, now with this, it doesn't matter where you put your Y's or your X's, even though it says Y varies directly as X. Generally, that would mean that you put your Y's on the tops and your X's on the bottom, but it doesn't matter, okay? So this first set, it says X is 5. By the way, that should be an ordered pair. Like if you were to graph that, you'd have an X that's 5. I've got my X on the bottom, and when the Y is 40. So I've got my Y's on the top, okay? Again, if you have that flipped, it's okay as long as your other fraction is flipped as well. The next one, it says find the Y. So again, I got my Y's on the top when X is 2. So my X is 2, it goes on the bottom. Then you solve this however you like to solve your proportions. Most students in the past are like, Mr. Sal, I'd really like you to use cross multiplication. I prefer fish method, but this is good too. So cross multiplication says you take the 40 and times it by the 2, and that should be exactly the same as 5 times the Y. 40 times 2 is 80, and that would equal 5 times Y. And then to solve that, Y, we would just divide both sides by 5. Just like you would an equation, right? So that's a phantom 1Y equals 18? Thank you. Math is hard. So use calculators. Please don't do that in your head like I did. And can we check this? Well, yeah. Just take your Y there and replace it with 16. 40 divided by 5, by the way, you would have gotten, if you had done that division, you would have gotten 8. But 16 divided by 2, also 8. Now we know the equal sign is true. And we found the appropriate and correct value of Y that makes it true. So we found the solution, and we can feel good about boxing that in. So that's one way to do it. The other way is to use well, I guess it'd be the proportional constant. This one, you can also solve for the proportional constant. So remember, K is the same as, it says Y varies directly as X, so that should be Y over X, I guess. And then the first value says Y was 40, and then the X was 5, so your constant, your proportional constant here is 8, which I guess what we got right there. And so or Y equals KX from that last slide. So we're solving for Y in this case. The K is 8, the X is 2 for that one. It's the green 2, which is 16. So you get the same answer both ways, but this one is using the proportional constant there in red. And again, the reason I bring that up, I never do it this way. I mean, you're welcome to do it, but I generally solve my proportions this way, but this is all in preparation for what we're going to see as joint variation. If something varies directly as X, the K is equal to Y over X. Really, this is the formula that you'd want to look at, that Y equals KX. Y varies directly as X. Now, if that was X varies directly as Y, then it'd be X equals KY, but whatever. Variation. This is the one that people tend to struggle the most with here, is the indirect variation stuff, okay? Now, we're showing the proportional, the constant of indirect variation, k this time. It's a constant of indirect variation this time. But k is x times y, whereas in direct variation, it's x divided by y, depending on how it's worded. But indirect variation means one group will go up while another corresponding value goes down. Indirect variation happens, I like to think of gas, not like, food you eat, but like gas, right? Like as you drive more, the more you drive, the less gas you have in your tank. That's an inverse or indirect variation. As one goes up, the other one goes down. Or the longer you spend at a grocery store, the less money you'll have in your account. That sounds good. Whatever, all right? Just examples, I'm just throwing those out there. So indirect variation does exist, but it, we can kind of formulate it like this as well. If that doesn't make sense, it doesn't have to. What we usually do is they're going to give us x and y values that correspond to each other. We find the k, and then we find usually it's a y value that's in there. But again, this is kind of the formula part that we're looking at when we get to joint variation, because it's going to join a direct variation with an indirect variation. But indirect variation is the division part of that. Y varies inversely as x. If x equals 2, then y equals 3, right? So on this one, again, we know the k is going to be equal to x times y. And on this one, we got a pair of x and y, right? That's a ordered pair. So the x is 2 and the y is 3. That's just 2 times 3, which is 6. So we know that our constant of indirect variation is 6. But then it says solve for y when x is 7. Okay, well, we know just from the formula, right? Even that it's just k equals x times y, we can formulate this into y equals it'd be k divided by x, which we saw on the last slide. So y should be the same as the k divided by the x. And we have an x value. Well, you could put the k value in first, by the way, but we got the x value at 7 right there. And we got a k value that is just 6. In my heart, I really want to just leave this as a fraction. But from what I remember on the assignment, except both the fraction and the decimal, I rounded the decimal though. 6 divided by 7, enter. Yeah, you could use, if you wanted to, the fraction or the decimal, 0.857142857. That's all my calculator shows me. And I believe I rounded it to the nearest thousandth, 10,000. But oh, okay. Yeah, thank you. So yeah, if it wants you to round, it will tell you either way, I guess. All right, so same thing on this one. It varies inversely, so k should be the same as x times y, and it gave us an x and y there. So on this one, we have the x value that's 5, so x is 5 there. And then we got a y value that's 10, so 5 times 10. Again, this is just to solve for the constant of inverse variation, which is 50. So it says solve for y when x is 13. So we know y is going to be the same as taking the k and dividing it by the corresponding x value, right? So we have the x is 13, so I take the x, replace it with 13. And yeah, the k on this one is 50, rather. Yeah, I can't, as a fraction, I know I can't simplify that myself. But as a decimal, looks like we get this one, 3.846153846. And again, you have to find out where it wants you to round, but either one of these should work on the assignment. But joint variation, if x varies directly with both y and z, then x equals kyz. That's a direct variation, by the way. Again, k is just the constant of joint variation. But sometimes what they're going to do is they're going to mix direct variation with indirect variation. So if x varies directly with y, then you'd have x equals ky. But if it also indirectly varies with z, then you get, it would have been x equals k over z. So we can combine those. We don't need two constants of joint variation. It's just k is the individual constant of variation on that. Now, you'll have to think about this too, because in this particular situation where it's worded, sometimes what they'll do is they'll switch the letters on us, okay? So what they'll do is they'll say, hey, find y varies directly with, instead of y there, you'd have an x and a z right there, something like that. In that case, your y would equal kx over z. So you got to be careful with the way these are worded. That's a z. But in addition to that, you have to be able to solve for k, because you're going to need the k on these, right? So I'm going to start with our original here. If we were to solve this for k, not fork, what we would do is the first thing I'd probably do here is multiply both sides by z. That would make that a phantom 1. Then you'd have zx equals ky. And then I'd say divide both sides by k so that you have just the y. So divide both sides by y. So at least you can solve for just the k. Now you've got k, because that's a phantom 1, equals zx over y. Kind of ran out of space there. A little bit better. Just keep that in mind. You'll probably have to solve for the k value first, and then you can apply that k to the new values that they give you, because they'll always give you a set, and then they'll say, find the missing value in the next set. Suppose z varies directly as x and inversely as y squared, and it's okay that it's a y squared on that. So the y squared thing, just know that's going to be part of what we end up looking at, okay? Now, it z varies with that other stuff, so my formula, if you will, give me z equals some stuff, okay? Now, it varies. First, it says it varies directly with x. So that means I would have to take my constant of joint variation, and I would have to multiply it by x. Then, it also says it varies inversely with y squared. So that means that I'd have to have a y divide by the y squared. Now, this is my formula for z. So, now, I need that constant of joint variation right there. So I'm going to manipulate this equation, just kind of like we saw on that last slide. I don't want that denominator there, so I'd at least start by multiplying both sides by y squared. And again, the reason what that does, it makes that a phantom 1. Now I've got yz. Don't forget the square part on that, thank you. Y squared times z, thank you, equals the k times the x. There we go. Yes, that's correct. So we're only one last principle of equality away to solve for the k. Simply divide both sides by x. So now I know that k is the same as taking your y, squaring it, timesing it by the z, and dividing it by x. So the k, right, we do have some values that we started out with. Right here. So I guess I'll do these in blue. So I do have a z value there that's 4, so I take my z from the k. I'm just solving for k, right? So I'm take the z, replace it with 4. I have an x value that's 2, so replace the x there in the denominator with 2. And then the y value is 3. Again, this is going to go in as 3 squared, though. All right, let's go to the calculator then. So 3 squared times 4 divided by 2, 18 is what I got. The constant of joint variation here is 18. Okay, now that I have that, I'm ready to solve for the missing z value. So that's that. I got to go back to this original. So I'm going to write it again. No, I didn't forget the square this time. So z equals kx over y squared, and we have those values. I'm doing it in orange. It says solve for z when x is 9 and y is 6. So I've got the x value. X is 9. And I got a y value, which is 6. And we can use this formula because we did already find the k value, which is 18. So in my calculator, I've got 18 times 9 divided by, it's 6 squared, so don't forget the square, because I almost did that one time. And I get a z in this one that is, I got 4.5. If you want the fraction, just push that double arrow button above enter, you get 9/2. But either one of these would work for your z value. Yeah, sales tax, state sales tax, T is directly proportional to retail price P. An item that sells for $170 has a sales tax of $10.22, $10.22. Find a mathematical model that gives the amount of sales tax T in terms of the retail price P. Okay. Well, if I were to find the sales tax right here, I would take the amount of tax and divide it by the dollars. That would give me the unit rate for the sales tax. I'm trying to think if that'd give me percentage. I don't think it would. I have to change it into a percent probably. Whatever, doesn't matter. So what I'm going to do is we got to have that mathematical model. So when it says mathematical model, it's talking about a function T of P on this one. Okay, so that means we got to have a P somewhere in here, but really it's just the price. You just multiply it by the sales tax. And the sales tax, should be the amount of the tax. The tax percent, I guess, would be taking the tax, which was the 10.22, and dividing it by, not a total doesn't seem like the right word. I guess the price, sales price, yeah, I guess price. Okay, so I know I can just take the price of whatever the item is and just multiply it by this, because that would give me the tax as a percent. So that's going to be $10.22. That was the tax. I don't need labels here, by the way, and divide it by the item, whatever the item's price was, which was $170. Okay, now that should make sense, right? Because it wanted the, let's see, mathematical model, sales tax. Yeah, we wanted the sales tax, so you need the tax per dollar spent on this one. But this gives us the mathematical model. Now we can use that model to find what the sales tax would be on $270. And I'm doing this knowing that you probably wouldn't actually do this formula, even if you were trying to find your own sales tax while you're shopping for some reason. But now you know you could. So now we got T of P. So let's set this function up. Okay, so I have exactly the same formula right here. But now I have a price of something. We want to know the sales tax on a $270 purchase. So the P now is $270. $270. And there's P right here also, $270. So I can get my calculator out. I'll use the fraction button, just because I guess that's kind of. By the way, I put this in the calculator. I got a really ugly decimal. That's why I'm using that as a fraction. But 10.22 over 170, 270. Almost used the original number there, didn't I? 270 now. No, it's this 170. I take back everything I just said. Now multiply that by 270. Enter, and we get another ugly decimal. That's okay. I got 16.231. So that I'm just going to round to the nearest hundredth because we're looking at the tax in dollars right here. 16.23. That's all we need on that one. This original fraction right here, if you changed it into a decimal, that would have given you the sales tax percent. Well, it still is a decimal, but 10.22 divided by 170. It gave me the decimal 0.06011767. And again, when I put this in the assignment, I kind of tried both, the fraction and this one. I rounded to this 100,000 place value, and it gave me full credit for it. So